Hello. So I'll be talking about the component-based UDEs with ModelingToolkitNeualNets. What does component-based mean? So first, as we've seen in the previous talks, we can describe physical systems with not just differential equations, but also with diagrams that can represent those differential equations. So in short, it's about representing dynamics of the system with components and connections. And they encode the physical meaning of the dynamics that are present there. As an example, Modeling Toolkit's standard library can provide such blocks. So here is an example of a thermal system, and we can see that we have various blocks, and then Modeling Toolkit transforms all of these blocks into a DAE system, so into a set of differential algebraic equations. And the advantage is that we can also represent this with blocks, as we've seen in a previous talk by Chris. And now, what happens when we go to Modeling Toolkit? Modeling Toolkit sees those all of these equations, and after simplification, we have only two differential equations, as you can see here. Now, going back to UDEs, what are UDEs? Universal differential equations. Usually, we've seen this formulation where we manually add a neural network term, or you can use other operations too, so that you enhance an existing known model with the output of a neural network that becomes embedded inside the model. But how can we do this with keeping the block representation, right? Because that block representation is very useful in working with the system and understanding it better. And this is what ModelingToolkitNeuralNets is for. So the idea is to have a system interface in Modeling Toolkit such that you get a system out of the neural network so that you can connect things and as inputs and as outputs. And this is just a normal looking system with MTK v10, where we have some equations, and as you can see here, the equation is just getting the output from the LUX model with the given inputs. We also have a callable parameter interface, so if you want to say NN of my input, then you just treat that as a callable parameter, so again, it's just a normal callable parameter in MTK. How does this work? So the important part in both implementations is that we have this stateless apply from LUX, which is just apply that only returns the first argument. And why is this important? Because by having this function, we can specialize the behavior to Modeling Toolkit such that we register this as a black box. So from the symbolic side, we only see that we have some black box function that is returning an array, and it's accepting an array. And that's all that we need. So how do we use this? We just build our model as usual, and then create a new system representing the network. And as an example, I'm going to take the thermal system presented earlier, generate some data, and then put a neural network somewhere inside the system, instead of the components that I had earlier. And if we take a look at this implementation, we can see that we create a LUX chain. We have to specify the number of inputs and outputs to the neural network block. And we have heat ports. Here, since we have a thermal system, we want to translate between the physical side of things. So we have heat and numbers, which are the neural network output. So we need essentially a translation layer between the physics land and dynamics land to the neural network land. And how do we do this? Is by the equations that we have here. So essentially, we need to think how can the physical part map to a neural network input that is valid for a neural network in the sense that it doesn't go outside of the bounds where the neural network is responding well. So it depending on the activation function that we choose, we have to potentially scale our inputs. And we also want to enforce maybe conservation properties from the output of the neural network. Or you might want to introduce additional states that are modeled via the neural network. So in this case, what I am showing here is adding a new state, that X, that is an additional state that we add to the model via a feedback loop. So essentially, we take the neural network input, and then we feed that into its differential. And with the constraint, what we want to do is to enforce the conservation law for the heat when the system is steady state. So essentially, we want a conservative component at steady state. And as I said earlier, we might also want to scale things. So when we put this together, we just have to insert our translator component that translates from the direct raw neural network to the physical system, and then we can continue to use this as normal. So we build a full system, we structurally simplify this, and we see that the thermal neural network, which is our translation layer component, enters the structurally simplified equations. Of course, this means that we can also represent this with the approach that I mentioned at the beginning, where you just you manually change your differential equations. But when you work with larger models, it might be more convenient to work at the acausal layer, so to work before you actually have the differential equations. And now it's just a simple parameter fitting problem, because we just have the weights of the neural network, which is essentially a vector parameter inside our system, and we are just going to train the neural network by building an optimization problem and then solving it. We have optimization.jl, which can help us with that. And here I'm showing a two-stage solving where you first do ADAM and then LBFGS. And we can evaluate the results and see that it fits well. And here is what we had before, and we can see that it trains and it is overlapped. Essentially, we can look at anything from the system, so we can directly compute either the neural network output or functions of the neural network output, depending on what we need to fit with. So what's next? We can either use the trained neural network as is, or go further and do symbolic regression, so that we take the neural network component and find an analytic expression that would map to what this neural network would represent. And in this case, I had a linear component, and we see here that we have one of the candidates that would represent the neural network is another linear function. This was a simple example, and I don't know if there's more time. Okay, so yeah, this is also available in DIAD, as mentioned earlier by Chris, where we have analysis that can build the neural network and to do the analysis of how would you do component UDEs within the DIAD framework. So yeah, that's all. Thank you for listening.
Thank you very much. We have time for one quick question. No? Maybe I have one. Maybe I missed something, so forgive me if it's the case. But the connection with DIAD, can you elaborate how we can use it?
Yeah, so the connection is that in DIAD, again, we have this block representation. We have the acausal representation of models, and we can also represent neural networks in an acausal way with DIAD, leveraging ModelingToolkitNeualNets.
Thank you.
Yeah, thanks.